All right, so now we're talking about logarithmic functions. Logarithmic functions are earthquakes that are measured on the Richter scale. A higher measure on the Richter scale means there will be more damage because for each increase in 1 unit on the scale, there is a tenfold increase on the intensity of an earthquake. Logarithmic functions help us understand diverse phenomena, including earthquake intensity, human memory, and the pace of life in large cities. Logarithmic functions are the inverse of one-to-one exponential functions, which means no horizontal line can be drawn that intersects the graph of an exponential function at more than one point. So exponential functions are one-to-one and have an inverse. Logarithmic functions for x greater than 0 and b greater than 0, where b does not equal 1, we have y is equal to log base b of x is equivalent to b to the y equals x. So as you pay attention to this, kind of notice where the placing is. We have a b, we have the x, and we have the y. So base b to the x equals y when we're talking about log. So log base b to the x equals y, and b to the y equals the x. So kind of notice how those follow in there. The function f of x equals log base bx is the logarithmic function with the base of b, and it's a little bit lower. It is not at the same level as the word log. The equations y equals log base bx and b to the y equals x are different ways of expressing the same thing. The first equation is a logarithmic function. The second is the exponential form of that. So here we have some basic log functions right here. So that'll kind of give you some ideas of what we're looking at. So log base 2 to the 16 is basically asking what exponent, what power gives 2 to the 16. So you can kind of look at those. We're going to actually do some problems to understand this in a little bit bigger setting here. So when we're looking at example 1, we're going to change from log to exponential form. So it's logarithmic, but I'm going to write log because it's a lot shorter to write. So the first example, if we have 2 equals log base 5 of x, I'm going to reverse the order just a little bit and put the equal to on the other side. So log base 5 equals 2. It's a little bit easier to see what to do with it. Now remember, they don't just switch places. Mathematically, there's this whole big explanation. But visually, what happens is that we have 5 to the 2 will equal to x if we change it to exponential. So 5 squared equals x. And we're not looking to actually find the value. We're just looking at what it would look like in exponential form. We do know that 5 squared is 25, but that's not what we're after right at the moment. So part B, we have log base B, 64 is equal to 3. Remember that B is a little bit lower than the word log. So this tells us that we have B to the third is equal to 64. In part C, we have log base 3, 7 equals y. So exponentially, we have 3 to the y equals 7. One of the things you want to notice is that the base stays in the same spot. The base doesn't move. The only thing that moves are the other two parts. They don't just switch. They visually look that way, but mathematically, it's more to that. But you need to understand visually that's what you're going to see and change. All right, so let's go to example 2. So in example 2, we are changing from exponential to log. So you're going to do the same thing we did, just slightly different. So for part A, we have 12 squared equals x. So we're going to change it to log. Our base is still here, so this is our base. And visually, the x and the 2 will change places. That's not mathematically, just visually. For part B, we have b cubed equals 8. So this will be log base b, 8 equals 3. For part C, we have e to the y equals 9. So we have log base e, 9 equals y. So now we're going to look at actually doing some evaluations. And this is what your chart looks like on your handout if you're in my class. So for example 3, so if you don't have the handout, I'm going to go over these examples, and if you do, you can kind of follow along with that. So example 3, we are evaluating logarithms. So I'm going to just put logs. We're evaluating logs. So for part A, we have log base 2 of 16. And we're trying to figure out what does it equal. So we can look at this as 2, because that's our base, to what power equals 16? Well, if we look at it mathematically, 2 to the 4th power equals 16. So 2 to the 4th equals 16. So that tells us that log base 2 of 16 is equal to 4. If we look at another one, part B, we have log base 7, 1 over 49. So we can look at 7 to what power gets us 1 over 49. Well, that would be 7 to, so 7 squared is 49, but because it's in the denominator, it's going to be 7 to the negative 2 equals 1 over 49. So that tells us that the log of base 7 of 149 will be equal to negative 2. If we look at part C, we have log base 25 of 5. So we're looking at 25 to what power equals 5? Well, the square root of 25 equals 5, and the square root has the exponent of 1/2. So 25 to the 1/2 will be equal to 5, because 1/2 is the same thing as the square root. So that tells us that log base 25, 5 is going to equal 1/2. Now, if we look at part D, we have log base 2 of the 5th root of 2. So we're looking to find 2 to what power equals the 5th root of 2. Well, the 5th root of 2 is 2 to the 1/5 power. So 2 to the 1/5 equals that 5th root of 2. So this is similar to the previous one. If we're looking at the square root, it's 1 over 2. The 5th root is 1 over 5. All right, so now we're going to look at some common log properties. So basic log properties involving 1. Let's see. So we've looked at the log base b of b equals 1 because 1 is the exponent to which b must be obtained. So to get that, we're going to have b to the 1 equals b. And log base b, 1 equals 0, because 0 is the exponent to which b must be raised to obtain that 1. So when we're looking at it, so b to the 0 equals 1. So if you ever have 1 right there, that's going to tell you you're going to be at 0. So some of our common logs properties, we have general properties where log base b of 1 equals 0. And that's the general property. The common log, which is where we have the log base of 10. And we have log base b of b is equal to 1. So when those match, they're going to be 1 because b to the 1 equals b. This would be log base 10. So if they don't give you a base, it is base 10. Log base 10 to the 1 equals 10. This is the inverse properties. So basically when this is happening, it's going to equal the x part here. And this, because the b's will, b to the x will equal b to the x. And b to the log base b, the logs are the base and what it's being raised to is the same, so it's going to be equal to that x that is there. Same thing will happen with 10 raised to the log of base 10 of x will equal to x. So let's look at those common logs in process here. So this will be example 4. So if we have part A, we have log base 7 is equal to what? So if we change this to exponential, we get 7 to what power equals 7? Well, 7 to the first power equals 7. So that's where we know it's going to be equal to 1. The second one we can look at is log base 5 of 1 equals what? So 5 to what power equals 1? Well, that has to be 5 to the 0. Anything to the 0 power equals 1. So that tells us that this is equal to 1. All right, let's look at example 5. So for part A, we have log base 4 of 4 to the 5th equals what? Well, it's going to equal the 5, because if you look at it, it'll be 4 to what power equals 4 to the 5th? Well, if this is 4 to the 5th, this has to also be 4 to the 5th. So we know that this will be 4 to the 5th equals 4 to the 5th, so that tells us that this will be equal to 5. If we look at part B, we have 6 to the log of base 6 of 9 equals what? And that's using those properties. So this here is using this property where log base b, b to the x equals x. Log base b, b to the x equals x. So this one is following on this one. So b to the log base b of x equals x. So 6 to the log base 6 of 9, this is going to be equal to 9. So it's following those same things. So we have some characteristics of log functions of the form f of x equals log base b to the x. So we've got the domain consists of all positive real numbers from 0 to infinity. The range is from negative infinity to infinity. So this is the inverse of what we see in the exponential functions. The graphs pass through the point 0, 1. And if it's b is greater than 1, it's going to rise up to the right in an increasing function. If it is a fraction, it goes down to the right as a decreasing function. The graph approaches but does not touch the y-axis. The y-axis, or x equals 0, is a vertical asymptote. The log function is the inverse of an exponential function, and the graph of the function is a reflection of the exponential at y equals x. So you can see here is y equals x. That means so if x is equal to 1, y is equal to 1. And this is the exponential. This is the log. Same thing happens over here. Over that y equals x, here are the reflections of each other. So here is your exponential, and here is your log function. So on our, let's look at some properties of our common logs there. We'll look at some more of those common logs that are happening. So example 6, part A, if we have log of 1 equals 0, remember this is log base 10 if they don't give us a base of 1 equals 0. Well, 10 to the 0 equals 1. That is true. For part B, if we have log of 10 equals 1, remember if they don't give us a base, it's 10, so log base 10 of 10 equals 1, so 10 to the first equals 10. Yes, it does. For part C, we have log of 10 to the x equals x. Remember, if it doesn't give us the base, it is log base 10 of 10 to the x equal to x. Well, if I take 10 to the x, it equals 10 to the x. And that is true. So 10 to the x equals our 10 of x. All right, let's look at part D. So in part D, we have 10 log of x equal to x. Well, again, if it doesn't have a base, it's 10 log base 10x equals 2x. And for part E, we have log of 100 equals what? So this is log base 10, because they didn't give us a base, of 100 equals what? So we can change this to exponential. So 10 to what power gets us 100? Well, we know that 10 squared equals 100. We could also rewrite that 100 as a base of 10. We could also state that log base 10 of 10 squared equals what? And then we can see 10 to the what equals 10 squared. So if that's a multiple of it, we can look at it in that respect. So there's different ways to look at that. And part F, we are looking at log of 1,000 equals to what? Well, this is log base 10, and 1,000 is 10 to the third, so that means 10 to what power equals 10 to the third? It will be 3. So the next thing we're looking at is natural logs. So with natural logs, the properties are similar, so log base b of 1 equals 0, well, the ln, that'll have the base of e, 1 equals 0. And you can see where this is the same here, this is the base of e, so these would be the same, it's still equal to 1. And the bases will be the same here as well. Now, ln and e undo each other. They do not cancel each other out. That's a key thing there. They undo each other. They don't cancel. So as far as our natural logs, we have f of x is equal to log base ex is the same as f of x is equal to the ln of x. So one of the things you need to remember is you can't take the log of a negative number. Just like in any of your square roots. You can't take the square root of a negative number. Alrighty, so if we're looking at example 7, we are looking at f of x is equal to the ln of g of x, where the domain of g of x is greater than 0. Remember, you can't take the log of a negative number. So it has to be greater than 0. So if we look at example 8, and we're looking at f of x is equal to the ln of 3 minus x, if we're looking at this domain, we're going to take 3 minus x and put it greater than 0 because that's what our function has to be. So we'll add x to both sides and find that 3 is greater than x, or x is less than 3. So if we're looking at our domain, we have our infinities on there. We need the number 3. X is less than, so it goes to the left. It has not an equal sign, so it's going to be a parenthesis. So our domain will be from negative infinity to 3. So looking at those properties of the natural logs, which we just went over, we have example 9. So in example 9, we have part A is the ln of e to the x will be equal to x, because the base, remember, is going to be the ln of base e to the x will be equal to x, because e to the x equals our e to the x. Part B, we have e to the ln of x will be equal to x because it's e to the ln, which has the base of e, of x, which then those will undo and you'll have x. For part C, we will have ln of e squared will be equal to 2, because remember, this has a base of e, so e squared equals e squared. And for part D, we have the ln of e 7x squared. So remember, this also has that base of e, so ln base e, 7x squared, so e to what equals e to the 7x squared? This will be 7x squared. So it follows the same things that we had. So let's do a quick review. We'll do a couple of problems. So this will be a review just to pull it all together. So if we're changing to exponential, if we have the log base 2 of 16 equals 4, changing it to exponential, we bring down our base. 2 to the 4 equals 16. If we are changing to log, then we have 2 to the 3rd equals 8. We have log base 2 of 8 equals 3. And if we want to evaluate, a log, if we have log base 3 of 9 equals what, then we can go 3 to what power equals 9? Well, 3 squared equals 9. So that tells us that this will be equal to 2.